Okay, so here we have an airplane in a crosswind, and the question is stated as such. Airplane's instruments indicate that its velocity relative to the air is 60 meters per second at 90 degrees. So in our usual coordinate system, that would look like, so if we put our, there we go, and that vector would look something like this. And we'll call that velocity of the plane relative to the air. So V sub PA, and it's at 90 degrees. And then it is determined that the air is moving 20 meters per second at 0 degrees relative to the Earth. Okay, so we can draw that a couple different ways. I'm gonna draw it like this, and we'll see why. I'm not doing that too well to scale, right? It should be about 1/3 of the length of the other one, but enough to get the idea. So velocity of the air relative to the Earth. And these, right, are 20 meters per second at 0, and this one is 60 meters per second at 90. Okay. And we're looking for the true velocity of the airplane, i.e. its velocity relative to the Earth. So plane relative to Earth, V sub PE, and we're going to figure that out. Now, if we put this into our usual relationship between relative velocities, sort of match that pattern, plane relative to the air plus air relative to the Earth, and we have both of the things on the right-hand side. We're putting in this pattern because these two, the air, that perspective, so to speak, that reference frame doesn't appear over here. And also this P is in the first position on both sides, and E second position in the second term on that side. So once we have that, we can see that this, the thing that we want, is just the vector sum of these two velocities. And I've already set that up in the diagram with the head to tail method so that we can draw in this. Now this, again, is not particularly well drawn to scale, so the angle that I'm representing here is unlikely to be very accurate in the drawing. But all we need to do is a 2D vector sum. And we even don't need to do a particularly complicated one because we already know the total x and total y component, because this one is all in the y direction and this one is all in the x direction. So we can skip right to one of the last steps in a 2D vector sum and just say that the magnitude of the plane's velocity relative to the Earth is going, oh, no arrow because we're doing magnitude, square root of that plus that, because they are the total x and the total y components. Okay, normally you can't skip right to this, obviously, but we can in this simple case. Okay, so when we do that, and with this set of numbers, you've got, let's see, 60 squared, and you've got 20 squared, and that gives you just a little over 60, so 63.2 meters per second. And we need to find out what this angle is. Let's go ahead and find, we can find a couple of different, let's find this one right here. And for that, right, we need that side and this side. That's just gonna be VAE down here, and this is gonna be VPA over here. And so when we go to get that angle, call it phi, like we often do. Just use inverse tangent of VPA over VAE, and that gives you inverse tangent of 60 over 20, which gives you an angle of 71.6 degrees. There we are. There's our vector.